it's true, but actually it's quantum repeaters embedded with quantum memory, so that's more accurate, I guess. Okay, we have discussed this quantum classical memory basically using electromagnetism knowledge. So we are using the right hat to just write the bit into the empty block, and then we can read out using the read hat. Of course, this is the right hat is made up of the changing electromagnetic field, which can hit or the bit in form of 0 and 1. So depending on the direction of the North Pole. And then for optical quantum memory scheme, basically, so it stores the quantum information in terms of qubit, quantum bit. So as you can see over here, the wave function basically is the superposition of 0 and 1 state, cat 0 and cat 1, and of course, I guess that cat 0 and cat 1 satisfies. Sorry, I think it's alpha and beta should be satisfied normalization condition, which means that alpha square plus beta square is supposed to be 1, and of course 0, the cat 0 and cat 1 is orthonormal. So this is basically what we meant by the qubit. And for this quantum memory scheme, or I could say quantum repeaters, we could implement the quantum entanglement later on, whereby two particles, or in this presentation, I will show the ensemble of atoms are interconnected even from a far away distance. So this is basically, I think you are familiar with this state. So this is one of the Bell state measurement, or also known as maximally entangled state. So later on, I will show how this entangled state is produced. And then we are going to use the concept of quantum coherence too. Last time I have talking about this. So it's the ability of the quantum state to maintain the properties such as entanglement and also superposition. Okay. Right. So classical repeaters. So I guess everybody has seen about or know about repeaters. So when we want to transfer information, for example, in photon or in using light, so we need to have a channel. So one of the option is to use fiber optics cable. So you can see over there, this is the underground fiber optics, but we know that this signal is susceptible for the loss or attenuation. For example, the photon or light absorbed by the fiber itself. So the solution is, what if we use repeaters, right? So classical repeaters simply it takes the signal, okay, coming from the one side, and then copy it and amplify it, then retransmit back at the higher power to the other side. But the problem, we cannot do this using quantum repeaters. Why? Because of the challenge is the no-cloning theorem. Sadly, quantum repeaters, okay, we cannot do the same thing as the classical repeaters can do because of the no-cloning theorem, so we cannot copy it. So what is no-cloning theorem actually? So let's suppose we have this phi. We start from an unknown state. So phi, you can express it in superposition of 0 and 1 basically. And then basically the idea is you want to have I forgot to write that. It's okay.
You need a pen?
Yeah, maybe I forgot to write the.
You can erase.
So basically, we have two qubits, phi and 0.
Can erase the other way.
Okay. So maybe I guess I'm going to prove why no-cloning theorems is why we cannot copy the state basically. So phi and get 0. So we want to copy it, become psi. So of course psi is just 0 plus maybe beta of 0, and then this is 0. So we want to, is there any like unitary operator that can do this? For example, can Hadamard gate do this, or can the combination of Hadamard gate and CNOT gate can do this. So let's see if we can do this or not. So of course I'm going to take this alpha 0 plus beta 0, sorry 1, sorry 1, and I'm going to so let's see if we can copy the quantum state. Let's see. So this is 0, 0 of course plus beta 1, 0. Can we? So this is alpha square 0, 0 plus alpha beta 0, 1 plus beta alpha 1, 0 plus beta square 1, 1. So of course this is in general is not true, left hand side and right hand side. It is only true when, for example, I want to have alpha equals to 0. So this is 0, this is 0, 0, 0. So this and this is not same also, right? And what if beta equals to 0? So beta 0. So this left 0, 0, 0. So it's only true when beta equals to 0, which means this is not the this is not superpositional state already. So we prove that the no cloning theorem is impossible. I mean, copying the quantum state is impossible. So we have the restriction of no cloning theorem. But it is not necessarily to have the repeaters which can copy this quantum state. We can use the advantage, for example, quantum entanglement and entangled swapping, which I will show you next in the next slide. So we have proof. Okay. So for the long distance communication, what if we use just fiber optics? Well, there are two research that I found on from the journal which have done this. They distribute entanglement over 300 kilometer fibers, and they use fibers to distribute quantum key distribution over about 307 kilometers. But what if we want to extend to 1000 or 2000? And of course, remember our major problem is for the optical fiber, okay, there is exponential attenuation or loss of signal over long distance. So we need to find a way to distribute the quantum key and also the entanglement over 300, maybe more than that basically. So this is our major problem. So this is the graph of power versus distance. We have learned this during our photonics class, I guess. So why would us bother to use quantum repeaters? Basically, this could solve the major problems of the exponential loss. Okay, what is the concept of the basic idea for this long distance communication? Okay, so what if we have this long distance, maybe A and B. Okay, so quantum repeaters, basically we divide this long distance, for example this is 1000 kilometer or 2000 or whatever. So we just divide into several segments. So which means we have maybe B and C, so we divide them. But this is not interconnected yet. So our aim is we want to connect this and this. So this is basically the quantum memory lah, basically. So this is quantum memory using atomic ensemble for my discussion or presentation today. Atomic ensemble. So, atomic ensemble. Okay, so A, B, C, D is basically the quantum memory. So we are going to store, you will see we are going to store the excitation state later on. And then our aim is we want to connect this first. And this, so we form a pair of entanglement between AB and CD, and then after that we are going to do the entanglement swapping between this and this. Then after all this, we are going to connect A and D throughout the entanglement swapping, as you can see over there. And then basically we already connect A and D, so we can do manipulation. For example, we want to distribute quantum key, okay, from Alice to Bob, and quantum communication, and so on and so forth. So that's our intention. We want to build the quantum repeaters with embedded quantum memory. Okay, this is the same thing. which I already drawn there. So how we are going to entangle this? We are going to implement the Bell step measurement. So later on, we are going to see about Bell step measurement more. And then the second step is to do the entanglement scoping. The intention is, yeah, of course, to extend the entanglement distance. And then after that, long distance communication can be established. Okay, atomic ensemble. So my focus is using atomic ensemble. Quantum memory, one of it is DLCM protocol. So the basic idea is what we are going to store is basically the collective excitation. Okay, so of course there you can see the optical transition. So you start with the atom, all the atom will be in the ground state. So you are going to apply the laser pulse, weak laser pulse, and then you transition. So this equation basically describes the collective excitation, which I will explain specifically for DLCZ. And so all of the atom basically in the ground state, but only one will get excited, denoted by S. I think this is EJ, not SJ. SJ is for DLCZ, so this is just in general for atomic ensemble. And we are going to store our collective excitation in the S state of that spin excitation state. Okay, to achieve efficiency basically in quantum memory, what I have learned, we need to have higher interaction between the single photon and also the atom, or the ensemble of atom. So we need to have the higher interaction, okay, so that the absorption of photon by the atom can be increased. So from my research, I get this equation. So this is basically probability scattering, which describes the interaction between the atoms and also the photon. And why we want to use the atomic ensemble, so which means many atoms, because we want to increase this. Of course, this scattering probability is proportional to this. So the higher this, the higher this, right? So of course, when you let this to be 1, this value will be reduced. Okay, when you have only single atom. So we want to have, that's why we want to have an ensemble of the atoms. Okay, so this is the paper. You can check on internet, online, or journal. So this is long distance quantum communication with atomic ensemble. You can read this is, I think this is the introduction.
DLCZ.
Yeah, DLCZ. So DLCZ is I think the surname of the the person who discovers Duan, Lukin, Sirac, and Zolker. You can check out the paper, and yeah, of course it's quite hard to understand, but yeah, I'm trying to understand it also. But what the idea is basically we want to create the single collective spin excitation. Sorry, that's typo. In atomic ensemble using weak off resonance classical paths. So what is meant by this? Okay, so what is meant by this? Okay, so collective spin excitation. So collective spin excitation is basically just the excitation of the atom over which shares coherently over all the atoms. So you have here, so this is basically the image or the picture of the quantum memory in the lab. I mean, not the quantum, the quantum memory. This is the ensemble of atom in cold atomic gas. So they are using cold atomic gas, but from my inspection, I found out that DLCZ can operate in room temperature too, not necessarily at cold atomic gas. Yeah, of course. We are going to, later on, I will explain more. We are going to apply the right pulse. Okay, right pulse, the atom will excited. Okay, the atom will excited to the excited state, and then it will release the Stokes photons. And this is where the spin excitation state is created. So the atomic ensemble is excited with a weak laser pulse, and in return, the photon will entangle. Here. Okay, so I think this diagram is better to explain. So you apply the right pulse, okay, and then the Stokes photon will will get released. I mean, will be emitted. But so what? So this detection of the Stokes photon will project, okay, the atomic ensemble into the equation above. So the equation, the most upper one is basically the spin excitation state, the similar one that I shown you previously. But over here you have the phase term, kW phase vector, kW minus ks, okay, which corresponds to the right pulse and also the for the Stokes photon, I guess. Yeah, and for the Stokes photon. So what the equation means is basically all of the atom in the ground state, and only one is get excited to the S state. Okay. So you can see from the diagram. So only one atom transition to the S state. Okay. And then this will at the same time, okay, this will create the entangled states between the Stokes photon and the atomic ensemble. So of course, this is described by this equation. So this is very familiar for us. And yeah, so far P there is basically the probability of small excitation to occur. And then when you want to retrieve this data or this information that you have stored in the spin excitation state, so you can apply the read pulse, and then anti-Stokes will get released. And then this spin excitation, that one that we have stored, will be converted back to this anti-Stokes photon. So that's the basic concept actually. Okay. And then of course it obeys the phase matching condition, kW plus kr equals to ks plus kan. So this is a right pulse phase vector, and this is read pulse, and then S is Stokes and AS is anti-Stokes. So if you observe here, so this is the final state after the reading process. So kW minus ks, if you insert, for example, kW minus ks over here, so this will becomes 1. So the state will just summation from 1 to NA, this. So this becomes 1 if you substitute this. Yeah, so that's for the reading and writing and reading process. Okay, so we are going to create the entanglement between ensemble 1 and ensemble 2. So this is the writing process. So we stored the data already. Okay, we have stored the data. So what's the next step is our goal is to entangle the remote located from at a far distance 1 and 2. So we have here the Stokes photon from the memory 1 and memory 2. Okay, we are going to interfere or combine at the beam splitter. So the detection of this the detection of this Stokes photon will be either in detector 1 or detector 2 only. So it cannot be both. So this will give rise to the heralded entanglement, which means that once the detector, either detector 1 and detector 2, clicks in either detectors, so this will indicate the creation of entanglement between memory 1 and memory 2. And then the state is described by this. Okay, so A and B is already entangled. So yeah, we do this already. So this is our first step. Okay, A, B, and CD. So we can do the same thing for CD. So done. So this is one of the Bell state measurement. Maybe we can revise back Bell state measurement for our exam. Yeah. So how the Bell state measurement was done is basically we are using the Hadamard gate and also the C0 gate. So Hadamard gate provide will prepare the qubit into superpositional state. Okay. So for example, if you start from 0, so you have a superposition of 0 and 1, and then when you start with 1, so you have 0 and minus 1, okay, with the normalization constant 1 over square root of 2. And then C0 gate is basically how the C0 gate goes or be used is basically we have a control and target. So when the control is 1, we are going to flip the target. Okay, so control 1. So the target is flipped from 1 to 0 and from 0 to 1. But if the control is 0, so there's nothing happens. Okay, and this is combination of this, we can create the four bell step measurements, the 4 bell step over here. But we are only using this one. Okay, only 1 0 and 1 0 and 0 1. That's all. One of the bell step. Okay, so this is actually the image taken from the lab. So you can see this is the first quantum memory over here, and then the second one is up there. So they are basically entangled, as we have seen, L and R entangled. So it's not quite far. L and R is not quite far. It's just separated by several meters, maybe 3 or 4 meters apart, right? It's not quite far. So yeah, maybe our job is to try to create entanglement at further distance. So the condition for this to happen is we have to coherent superposition, as we have seen, and then single excitation regime, whereby P equals to 1. So P is basically the parameter that I've introduced just now, the probability of small excitation to occurs in the ensemble. Okay, so one quantum of excitation shared between two quantum memories, of course, because they are already entangled. Okay, so let's do entanglement swapping. Okay, now we are going to do the read out mechanism between B, memory B, or ensemble B and ensemble C. So we are going to introduce the laser read laser pulse. Read pulse is applied to the ensemble, and then remember what we have stored is the spin excitation state, right? So we want to retrieve back and convert the collective excitation into the anti-stop photons. And then we combine through the anti-stop through the beam splitter. So basically, same thing, bell step measurement. Okay, at detector D1 and detector D2. Okay, the emitted anti-stop photon from ensemble B and C are combined at the beam splitter, and photon will interfere. So the detection of photon either from the detector D1 or detector 2, which of course there will be a click which indicates that the detection event or the heralded, so this is the terms is basically heralded event, projects the state of the remaining ensemble into entanglement state, which means that A and D is now in the entanglement state. Okay. So this is initially A, B, and C, D entangled, and then the final state A and B will be entangled. So you see the act of doing the measurement, okay, of this entangled A and B, entangled pair of A, B, and C, D will project, okay, or it will collapse because we are doing the measurement and we'll create a new entanglement state between A and D because we are doing the measurement, right, of the entanglement pair A, B, and C, D. We are doing measurements, so the wave function collapse, the entanglement state will collapse, and then it will create a new pair of entanglement A and B. So we do the bell step measurement here, and then we are going to create the entanglement between A and B. So this is at a long distance. So of course this is just oversimplified diagram. Of course you have very much distance apart. So of course you are not having this pair. So maybe you have A, B, C, D until Z. So we combine this using entanglement swapping. Okay, so it's very
this vacuum state belongs to A and D. It belongs to A and D, right? You create photon, one photon at A, one photon.
Yeah, because there will be either photon at B and C, right? So it belongs to A. I mean,
After bell state measurement.
yeah, after the bell state measurement. So this is the initial state, which means the entanglement between this is the pair, the first pair, and then this is the second pair. After the heralded photon is detected in the detector D1 and D2, A and D will entangle eventually.
So how do you write the full state of A and E entangle?
The full step.
It's like 1, 0 plus 0, 1, something like this.
Yeah.
Or 0, 0 plus 1, 1.
Yeah, because this is the equation presented in the. So this is the excitation creation at A, and then this is the creation. This is because this is the creation operator excitation created at A and B, basically, from what I understand. So which means the excitation we created there and there because of this creation operator.
So it's basically it's like this. PR. So A, D. So we have the state measurement. Like this one.
Oh yeah, something like that. Basically, what we are doing is basically the Bell step measurement between the.
So it's basically a entangle swapping.
Yeah. Okay. Okay. So I think. Okay, this is the summary what we have done. So write stores qubit in the spin excitation state. Then we do entanglement. After that, we do the read procedures. Then entanglement swapping, and then we can extend. So see, this is the memory that we do the Bell step measurement, and then the one which entangles at the end eventually is memory 1 and memory 2 over here. Yeah. So after the Bell step measurement. So this is the summary. So yeah, of course we already form a long connection, but is it efficient enough? Okay, basically from my readings, there is another way to do this, or the entanglement swapping. So this is more favorable from what I read. So this is the more favorable method. So just now we introduced the number state entanglement. So it's not practical according to the paper, I guess. The alternative way to do this is to use the two-chain implementation. So you prepare the two chain over there, which entangles A1 Z1 entangles A2 Z2, described by this equation, I guess. Yeah, equation. And then after that, we are going to read out. We are going to do the read out procedures, whereby we implement the read pulse, and then we do the Bell step measurement over there. So the anti-stop photons will interfere, and after that you have the effective states. So actually, my interpretation of this equation is basically you create excitation at Z and A, Z1 and A2, Z1, A2, and then you create the excitation state at Z2 and A1, Z2 and A1. Then you summing them up to create the effective states. So this is just my interpretation. So you can read over there. It's from the paper. The collective atom excitation on each side are transferred to the optical excitation, which respectively after a relative phase shift. So this filter phase, which impose the phase shift. Yeah. Yeah, we have done basically. So we are going to look at the advantage. What is the advantage of DLCZ protocol? Of course, it's favorable for quantum communication, quantum distribution, and remember, we already formed this entanglement between A and D. So remember, our friend has presented the QKD, okay, the ICAT protocol, the ICAT protocol, and also I forgot what
protocol. Who presented?
The Hun. So BB81, E91, yeah, enter. So you can check out his YouTube channel. then because we have four, sorry,
who presented it?
Pony,
Ah,
yeah, the quantum key distribution anchored protocol and also the BB, yeah, Bennett. So I forgot that name, Bennett. I just remember that. Okay, so because we have formed this, so of course when we want to do the quantum key distribution, we need to use both classical channel and also quantum channel. So Alice will transfer his, for example, state so that Bob will do the measurement, and then we'll do the measurement. Of course, we start from, we need to have the particle to be entangled between Alice and Bob first. So that's the first idea of teleportation. And then Bob will do the measurement, the measurement to perhaps to adjust because the state which, for example, okay, Alice will send 0 plus beta 1. So Alice will send, for example, this to Bob, but this is not the actual state. Maybe you need to do the unitary operation to swap the sign so that it will match with the state that Alice wants to transmit or wants to send, right? And yeah, scalability and room temperature operation, as I already talked just now. It can operate in the room temperature, not in the cold gas mainly. Okay, what is the drawback? So there's a research. So the point number 5 over there. So the storage time which they can reach, okay, is only 100 milliseconds. So it's very short time and low retrieval efficiency. So this is one of the drawbacks. So of course we need to have higher efficiency of the retrieval, the reading during the reading mechanism of the atomic excitation. And then, of course, it is susceptible to environmental coherence, which means that the quantum ensemble, the atomic ensemble can decohere due to the environmental factor. It can interact, and then the entanglement can collapse. Okay. Second point is photon loss sensitivity. So this is basic, and couponometry is detection efficiency. So we need to have a good detector and high efficiency detector, which is, I think, one of the drawbacks too for this. And then, oh yeah, you have seen that the entanglement can be created only at a shorter distance apart over here. So this is one of the drawbacks. Why not we can extend this entanglement distance, right? Maybe in future. Okay, so yeah. Okay. So this is just a conclusion I've taken from the paper basically. So the proposed technique allows to generate and connect the entanglement and use it in quantum teleportation, basically quantum communication. The overhead required to implement the present scheme, such as the communication time, scales polynomial with the channel length. So this is in contrast with what we have seen for the photonic channel, the fiber optic channel. So the attenuation varies exponentially with over long distance. So our homework is to improvise, perhaps to modify or whatever, to upgrade this DLCZ scheme so that it has longer coherence times, so it can store information and storage time will be increased, and then to reduce communication times to reach at longer distance. So of course we don't want takes longer time to transmit the information, okay, even over the long distance. So we want to reduce this communication time. And with that, yeah, this is the reference. You can check out the reference I used to make this presentation. Yeah, thank you very much.
So you want to reduce the communication time, or you thought you have quantum memory? Where is the function of quantum memory? Does it make use of quantum memory at this stage?
memory is okay. So what we do is basically we impose the write pulse, and then this write pulse will transform the ensemble into collective excitation state. So this collective excitation will be stored in the ensemble. Why? Because that's a requirement to create the entanglement between the ensemble A, B, and C, D, and border swapping. So that's my understanding so far.
So basically, this scheme is to create entanglement swapping. Right?
That's from my understanding.
It doesn't. Yeah, but the interaction with the atomic gas part, does it analyze the storage time? You mentioned about storage time.
Yeah, storage time.
But in one, what it would be an optimum? What would be the optimum storage time?
So from the research paper I read just now, so it's only that's the paper maybe 10 years ago. So and 100 milliseconds. So I don't know if that's the maximum. I don't have the theory or formula to prove what is the maximum storage time, unfortunately.
Yeah, it's okay, but nowadays there are people who extended it until days.
Oh,
So
maybe that's
yeah, if using some technique that they can store until days, they still can retrieve. But what's the point of storing it so long? Still,
there's no
right? Because if you use it as an optical buffer, you want to, right? It's like traffic come, the traffic light, you wait for the other traffic, and then you get right time. But it should be used as a signal, as a delay to synchronize the photon before the Bell-state measurement. Otherwise, why do you want to delay? Why don't you just go through, right? So what is the main reason of having quantum memory? Why do we need quantum memory?
Yeah, because from my understanding, because of we want to store the spin excitation state in the ensemble, and then this is important because without this, the stocks and anti-stocks photon cannot be created. And without this anti-stock and stocks photon, we cannot entangle this memory A to memory B. So that's from my understanding so far. Okay.
So we mean cannot entangle. Mean more specifically, entanglement is established when they do Bell-state measurement. So what is the requirement for Bell-state measurement? Two photons must come at the same time, right?
Yeah.
So for it to come at the same time, what do? You need to synchronize it.
Yeah.
You need to have. How do you synchronize it? Using quantum memory, right?
Oh yeah.
Does it make sense? So that's why you need to argue it in that way to really understand. To really understand. Otherwise, we still not clear why we want to do this work.
Yeah, because from my understanding, the memory is important to create the stocks photon during the writing mechanism, and then it stores this what's called the spin excitation step there, and then we are going to read out so that the stock photon creates. So that's all I understand from the paper too.
Because of the you want to synchronize lah.
Yeah, no, I know.
Then that's why we did a quantum memory. Otherwise, why you want to store the light inside and then wait? You if you want to create entangled photon only, you can create using parametric down convolution. But there are schemes where they don't use quantum memory.
Oh.
It is memoryless. But is it sufficient? No? Can you control? You want to have a controllable retrieval on demand. It's a photon on demand. You want it to come, it will come. That's the on demand.
Oh.
Because normally photon is all random, right? All random.
Yeah.
But in a double Raman scheme that we have been studying, that you can excite it and you can on demand the photon will come, right? So this has been done experimentally, but it has not been developed into the technology. This is what they can do can extend to make a long distance quantum internet. So that's the thing we have been doing the double Raman thing. Want to okay, good.
All right, bro. Thank you.
So the double Raman, the Stokes and Stokes. You want to wrap up the theory, a lot of theory already done. You want to wrap up the theory, maybe see, and then we want to do experiment. During holiday, if you are interested, anybody interested, all of you by kampung. Maybe you come back 1 week. If you come back 1 week before the school starts, at least we can do something. Yeah? Or maybe a few days before, maybe 1 week, maybe difficult. When are you coming back? The orientation week. When are you coming back next semester? Everyone? No plan yet. But do you think you can come back 1 week during orientation?
1 week before the semester starts?
During orientation week, because after orientation it will be first week of the semester already, right?
Yeah.
So at least during orientation week we can come, we can do something. Maybe okay, this one you guys can decide. Actually we during holidays what you plan to do? I plan to organize a conference